Well, that was unusual. I was just greeted to a computer voice that hadn't happened before. And good morning and welcome back, everyone. I, sorry about Wednesday's issue. Believe me, I had no intentions of canceling Wednesday's class. I had been told we were allowed to be on campus as faculty. Security guard let me in, and then an hour later, same security guard booted me out. So that was a fun experience. But I got set up at home now, so everything is fine moving forward. Before we start class, I want to put up a couple little memos. First of all, my math lab, they did some server maintenance or something yesterday, and per usual, it's kind of spilling over into today. It, I was not able to get it working this morning at like 7 a.m., but when I just tried to load our class about 10 minutes ago, it was working. So fingers crossed, maybe our class is resolved, but I can't promise that from student to student. It may be down for part of today for you. This is again another reason to emphasize, don't wait till the last second to do your assignments. It's not acceptable to say, oh, well, my math lab was down the last 2 hours of when this assignment was due. So can I get an extension? Well, no, you had days and a week or more in many instances to get this stuff done. So please make sure that you're staying on top of things, getting things done in a timely manner, etc. I have mentioned that I'm going to occasionally throw little quiz questions into our lectures, and I will not always announce these at the beginning of the lecture from now on. This is just to kind of make sure that people are watching these lectures either live or catching it on YouTube within the next 24 hours. So because this is the first one, I will warn you that at some point today, I'm going to just randomly kind of stop and say, here's a quiz question, here's the answer. It doesn't even have to be math. It might be just a random word is the answer. Spoilers for today. So you will, if you go into Canvas, into our course, if you go into the quizzes section, I believe I made it the very top. You'll see a quiz for 3:30's lecture. It's due 3:31. It's due by midnight. So make sure that you complete that quiz. That will be I don't know if I want to call these quiz grades or if I want to call it participation. I think I'm going to still call them quiz grades, but I want to talk to another professor or two and see what they're doing, just so that we're all on the same page. I'm also going to open up a new discussion board soon for one of these worksheets. There was pretty good participation. I would say about where I expected. Some of you did not answer anything yet, and that's okay. But remember, make sure that you are ultimately participating. I don't need everybody to participate in every single one, but if I find a student, if I do 10 of these and there's a student that's only participated in one, obviously you're not going to get full credit for that participation. If I see a student's only done 2, it's still a little low. So, participate in about every other one of these and you'll be fine. I'm not looking for absolute 100% participation every time. I'm not looking for you're always giving answers. You can ask questions, but I do need to see some discussion. This is basically akin to us being in class and working in groups. It's just one big giant group. And again, pretty good work on that first one. I just saw a few minutes ago that there were new posts. I haven't looked at them yet. I'll work on that later today. In the midst of the chaos from last Wednesday and me trying to get set up and deal with my other classes too, I never put in the due date for 4.2's homework, so that's going to be due the same day as 4.3, which will finish today. And so my math lab, 4.2 and 4.3 homework will be due in 1 week. Don't forget our project is due coming up as well in about a week. And I don't think I've given you an Excel assignment since the last one was due, and I don't have one to give you today, but I should have one next class. I will have our next Excel assignment, I believe, for next class. Okay, so with that stuff being said, let's pick up where we left off in 4.3. Again, 4.3, percent change and difference. So just as a reminder for some of these, quote, formulas, or as I like to call them, concepts, we said that total change is the difference of old and new. Now, generally speaking, we can call them old and new, but sometimes there is no time element. It's just thing 1 and thing 2, and then you have to decide which one's the old or which one's the new, or somebody else will tell you to consider this one as the old. And there's a worksheet involving that. So total change is just a difference of two things, whereas percent change is a ratio of the total change, that subtracted quantity you just found, divided by the original, and then converted to a percent, because you'd have a fraction originally. If you call something percent change, you should probably turn it into a percent. I think that just makes sense. And then we did a problem, the 20 students into 30. We saw that it was a percent increase. We saw it was a 50% percent increase as well. It was a 10 student increase, but a 50% increase because we went from 20 to 30. Half of 20 is 10. 10 is the number that was added to class. 10 is 50% of 20. We introduced that arrow notation from the text where we had the old on the left and we pointed to the new. I'm gonna scribble up here really quickly just what that was. We had old, then an arrow, and that should point to the new. On the top, we had the total change. On the bottom, we had the percent change. And that's always consistent. The total change always goes top, percent change always goes bottom. And I mentioned that I've never seen this notation anywhere besides this textbook or worksheets, but unfortunately, you'll see them in my Math Lab homework, so you do need to understand just where everything is. Okay. Then we talked about the growth decay rate. So if we say something goes up by 5%, that'd be 0.05 as a decimal. And we can take a growth or decay rate and turn it to a growth or decay factor by adding 1 or 100% to that value. Now that's if it's growth. If it's decay, you're supposed to take the 1 or 100 and subtract it. So a 5% growth means that the growth factor is 1.05, 1 plus 0.05. A 5% decay would mean that the decay factor would be 1 minus 0.05, and that would actually be 0.95. So decay factors always end up being something like 0.8 or 0.9 or 0.7, a decimal less than 1. Whereas a growth factor means you got more than 100% of something, it always ends up being 1.0 something or 1.2 or 1.5 or whatever. So the word factor in math means multiplier. So if you know the old and you know the growth or decay factor, then you can find the new by just multiplying those two things. And that is a concept that we're going to hammer over and over and over and over in the next coming chapters. This is one of the most important concepts we get into besides proportions. So this new equals old times growth factor. New equals old times growth factor. This is an equation that you're going to hear me say 50, 60, 70 times. If we were in class, I'd ask you 50, 60, 70 times about it, but I don't have that option right now. I can just say, what is it, and hope that you're answering over the internet. But again, this is a great way of going between new and old. And you don't have to have the old to find the new. You can have the new to find the old. It just involves a little algebra. So that's what we mentioned here. You could be given the new or the old and asked to solve for either. In fact, I can give you the new and the old and ask you to find the growth factor. And then from the growth factor, you can find the growth rate. All of these flow together. So let me see if I can just get this on one page. There we go, with all our different examples. So this would be group work, unfortunately. It's not now. We're just going to talk about these examples together. We're one big group and I'm the leader. We already did example 2 with an old salary of $55,000. We found that with a 7% raise, that made our growth factor 1.07. And when we multiply that by the 55,000, we ended up with $58,850. Check out last class's lecture a week ago to see that work. Again, really quickly here. Your growth factor was 1.07. That was the 1 plus the 7%. 1 plus 0.07. That is a 0. So the new was the 55,000 times the 1.07. The old times the growth factor. and that turned out to be units $58,850, right? Right. So that was the new. That was how much you had after your raise. Example 3 is a little different. Your new salary, come on, let me copy. There we go. I'm gonna try something. Your new salary is $71,500 after earning a 10% pay raise. What was your old salary? Let me see if this works. And paste does not work when I switch to the whiteboard. Darn, okay, let's try something different then. Let's just put some space up here. Okay, your new salary is $71,500. So that's our new salary. After earning a 10% pay raise, which is 0.1 when you convert it to a decimal. Our percents need to be converted to decimals to be doing this math. So they want to know what is the old salary. This is a very different problem. Last problem we were given the old and the raise and asked to find the new. Now we're given the new and the raise and asked to find the old. So we got to make sure we're plugging things into the right spots. We're going to be plugging the new into where it says new, and this 0.1 would go here as part of the growth factor. So we get 71,500 equals the old, we don't know that, so let's call it X, times parentheses, 1 plus the growth rate of 0.1. Again, that 0.1 right here was the 10% pay raise. We added because we got a pay raise. If I said we got docked, then we would have subtracted instead. Well, 1 plus 0.1 is 1.01. So that's 71,500 equals X times 1.1, or 71,500 equals 1.1X. Now, in example 2, we multiplied the numbers because they were on the same side. This one is not that case. We need to divide both sides by 1.1 to solve this. So that says, and if you do 71,500 divided by 1.1, you should get 65,000. So that's our X. Now, what is X? X was the unknown, that's the what, that's the old. So our old salary was $65,000. Then we ask ourselves, does it make sense? Well, the old salary is less than the new salary, so that's a good start. If you found that your old salary was more, that would not make sense since you got a pay raise. So let's say that you put the 71,000 on the right-hand side and you multiplied it by the 1.1, excuse me. So if you took 71,500 and multiplied it by 1.1, what you'd get is 78,650. How would your old salary be $78,650 if your new salary is 71,000 and you just got a raise? That sounds like a deduction to me of about $7 grand, in fact. Pay raises are not going to make your pay lower. Even after taxes, no matter what anybody tells you how taxes work, that's not how it works. If you end up in a new tax bracket, you're only paying that extra percent on the dollars in that bracket. But we might talk about that another day if we have time. So yes, this makes sense. Now, if you came up with an answer of say $6, that wouldn't make sense because $6 getting a 10% pay raise takes you to 71,000. No, sir, no ma'am. If you got an answer of maybe even $10,000, $10,000, 10% of that would be 1,000. That would only take you to $11,000. So these are in a ballpark of what we would expect for the numbers. 10% of 65,000 is 6,500. And if you add 6,500 to 65,000, guess what you get? 71,500. So it does work. All right, now I have to erase my screen so I can go to the next example. Example 4, your boss scolds you and takes 15% of your pay. So you have messed up severely at work. Or what's relevant right now, we got COVID-19. We got a lot of people that are taking pay cuts to kind of help everybody out, make sure that the companies are running. So maybe your boss is just taking 15% of your pay to keep the company afloat right now. I wish I'd actually updated that problem to make it more relevant, but at least I said it. So you made $12.50 per hour before. Now, the previous two problems I gave annual salaries. This time I gave an hourly rate per hour rate. Does that matter? Does that affect anything? Honestly, no, it doesn't, as long as you answer appropriately. So we want to know, what is your new rate? Now, we just got a pay deduction for whatever reason. We made $12.50 before. Does that sound like old or new? Old or new? Before makes it sound like it's the old amount. The 15% as a decimal would be 0.15. And that is going to be a decay. That's a loss of pay. So if we made 100% of our pay before, now we're going to make less than 100%, which is why we subtract it in this plus minus symbol. And we're not doing both. This isn't some quadratic formula. It's saying one or the other. So we want to know, what's the new pay rate? That's the unknown. So we go new equals the original or the old, which was $12.50 per hour. Then parentheses, 1 minus, because this is decay, we choose the minus instead of the plus, and then 0.15. 1 minus 0.15 is going to be 0.85. So the new should be 12.50, or just 12.5, then times 0.85. And if you do that math, 12.5 times 0.85, you end up with 10.625. 10.625. And some people might say this is the answer. First of all, there's no units, so we got to make sure that the other thing was in dollars per hour. This should also be in dollars per hour. But I'm going to say that this is not a great answer because it says 0.625. We're talking dollars and cents. We generally round to the nearest cent. So that says that the new salary should be $10.63 per hour. Oops, didn't mean to go through that part, but that's okay. You can still see it. Does this answer make sense? Remember, every single time we do a problem, we're asking, does it make sense? Well, we got a pay deduction. This number is smaller than our old pay, so that makes sense. We got a 15% pay deduction, which is, I mean, it's a decent amount, but it's not a ton. It's not like we lost half of our pay. Half of our pay would have brought us down to $625. So I would say that this number is in the ballpark of reason. If you had added this 0.15 instead, you would end up doing 12.5 times 1.15. And if you did that math incorrectly, what you'd end up with is 14.375. So you'd think you're making $14.38 an hour after a pay loss. No, sir. No, ma'am. You are definitely not making more if your boss is taking a pay or giving you a pay cut. All right. So got to clear the screen. Example 5. Your salary in 2018 was $52,000. Your salary in 2017 was $38,000. What was the total change in your salary? What was the percent change in your salary? So I've asked 2 questions here. I didn't do that in the last 2 examples. This is also a very different type of problem. In the last pair of problems, last 3 problems actually, we were given either the new or the old, and then the percentage change. This time we're given the new and the old, but not the percentage change. So again, this is a different type of problem than before. We're not using this new equals old times 1 plus X percent necessarily. I'm not saying we can't use it. I'm just saying that it's probably not the best idea. What we need to go back to is the very basic idea of total change and percent change. We have to have our concepts down. We have to pay attention. We were asked to find total change and percent change. And we were given the new and the old. Well, total change is the new minus the old. Percent change is that ratio we talked about earlier. Let me copy this and just put it down here as a reminder. There we go. So again, these are the formulas we're using for this problem. This is a drastically different setup. So 52,000 and 38,000, which is the new, which is the old? Well, we were given years, so that would probably help us. 2017 happened first, so that's our old. 2018 happened later, that's our new. Now we're not using the 2017 and the 2018. We are not using the 2017 and we're not using the 2018. We're using the dollar amounts. So that's the new and the old. Total change is the new minus the old. That's 52,000 minus the 38,000. Which is, what's that, 14,000. That is our total change. That was one of the answers requested. So we got a pay bump, a pay increase of $14,000 from 2017 to 2018. That kind of sounds like we got a whole new job. The next question is, what was the percent change? So percent change makes this relative to what we had in the past. That's why that ratio is the total change to the original. It's not necessarily over the smaller, it's not necessarily over the larger, it's over what happened first. And what happened first was the 38,000. So total change we just found to be 14 grand. That's the top of the fraction. Over. The original, that's what happened first, and that was the 38,000, not the 52,000. And you could reduce this if you really wanted to. All the zeros are gone. It's just 14 divided by 38. You could reduce that again, and that's 7 over 19. But if you do 14,000 divided by 38,000, you'll end up with 0.360. Now I'm going to put a whole bunch of these up here. 36842. But that is not a percent, that's a decimal, so we have to convert that to a percent. Decimal goes right twice. 36.842. And let's round this to the nearest tenth of a percent. Oh, I forgot my percent symbol. Rounded to the nearest tenth, that makes this approximately 36.8%. If you round it to nearest tenth, I'm sorry, the nearest whole would be 37%. And that was an increase. Both of these were increases. You can't have a total change that's an increase and a percent change that's a decrease. That's literally impossible. Does this make sense? Well, the difference of the two is definitely 14,000. That should be obvious. The percent change, well, going from 38 to 52, if we had 100% salary increase, that means we double our salary and it would bring us to 76,000. 52 is a significant increase, but it didn't take us to, what did I say, 78,000. That's a little less than half of a gain. Half of 38 is 19. And if you added 19 to 38, you can see it would be less than 52. So this does seem to be in the ballpark of reasonability. But again, this example 5 was drastically different in approach than examples 1, 2, 3, and 4. Because we were not given the percent change and one of the new or the old, we were given the new and the old. Given the new and the old, we can find total change. Once we have total change and the old, we can find percent change. Make sure you're converting your percents to decimals. Make sure you're rounding as my math lab asks. why, if you use, someone just asked a question, why if you use the whole number you get 36842? I'm not exactly sure where you came up with that. This division of 14,000 and 38,000 definitely gives a decimal of 0.36842. And then when you move its decimal right twice, you get the 36.842. You're not going to move it right 5 times. Oh, 3.6. Again, if you check your math, 14 divided by 38 or 14,000 divided by 38,000 is still going to give you 0.36, and the decimal goes right twice. It sounds like you're only moving the decimal right once, or you're doing your division inaccurately. So please check your work. Again, 14 divided by 38 would still be 0.36, etc. All right, let's clear our screen. Take off annotate. Delete, delete, delete. There we go. All right, example 6. Very relevant for some of us. The stock market's a little crazy right now. It's very volatile, which means subject to rapid change. You have $100,000 in mutual funds. So you've been putting money away in your retirement for quite some time, and you've got $100,000, which is pretty good. You're not necessarily going to retire on 100 grand, but you're working towards it. On Monday, you gain 50%. So on Monday, just this one day alone, you gain 50% in the value of your funds, which is absolutely bonkers. This is not something that's typically going to happen on a mutual fund. But for the point of this example, we'll say it happens. Then on Tuesday, you lose the exact same percentage amount, but instead of a gain, it's a loss. And then the question I ask is very quantitative reasoning. Are you happy, sad, or indifferent? So, kind of subtle questions. Oh, I'm happy because I still probably have a whole buttload of money in there. Sad could be, oh, I don't have enough. Indifferent, I mean, yeah, I understand that these are interpretable, but what I'm basically saying is, did you make more money in the end? Did you lose more money in the end? Or did you end up being the exact same? That's what I'm trying to say. And then as a part B, we'll say, what if we reverse the order of this? Does that change the outcome? So let's call this part B. Part A. So we have $100,000 in mutual funds. That's our old value. Then on Monday, we gain 50%. That's our percent change, but as a decimal, that would be 0.5. On Tuesday, you lose 50%. Okay, this is 2 different days. These are 2 different percent changes. These are 2 different problems. So we're not going to be able to do this in one step. It's going to take 2 steps. We have to do the math for Monday, then we have to do the math for Tuesday. So on Monday, our new amount would be equal to the old amount, which is 100,000, times, well, parentheses. Then this is a gain, so that's a growth. So we go 1 plus 0.5. That's the 50% gain, so that's a plus, which would be 100,000 times 1.5, which is $150,000. So that's what we have on Monday. Now, at the end of Monday, we're very happy. We just increased our mutual fund money, our retirement fund, by 50%. We went from 100 grand to 150 grand. Absolutely insane. Again, this generally does not happen. But then on Tuesday, and let me switch my color. On Tuesday, we saw a 50% loss. So this is still 0.5, but that is a decay, whereas the red was growth. So on Tuesday, our new equals the old times the decay factor. but the old is no longer $100,000. We don't have $100,000 on our account anymore. We now have 150,000. So this number right here is the old number for Tuesday. We've seen this concept many times in finance where the new amount for year one is the old amount for year two. So we're going to use 150,000 for our old. We're going to use 0.5 as a decay factor so that the new is going to be 150,000 times 1 minus 0.5. Again, minus because decay. Now, these 0.5s are not identical because we're just using one of them. Again, it was a gain of 50%, then a loss of 50%. I could have said we gained 50% Monday, then lost 10% Tuesday, and now this would just be a minus 0.1. So make sure that you understand these are not always going to match. Well, 1 minus 0.5 is 0.5. So this is 150,000 times 0.5, basically saying that we're going to have half of the money we previously had. We previously had 150. Half of that's 75 grand. So now we only have $75,000 on Tuesday. So are we happy, sad, or indifferent? I mean, you could say I'm happy because I still have $75,000, but my frame of reference is I'm sad because 2 days ago I had 100 grand and now I've only got 75 grand. So I'm sad. That's my personal opinion. So again, this was an iterative problem because there were several days worth of percent change. So we had to do the calculation for Monday, and then we use that number because the new on Monday is the old on Tuesday to be able to work on Tuesday. So now if I said on Wednesday we gained 10%, are you happy or sad? You'd have to go through this whole thing again. So let's hold on to this number. At the end, having the gain and then the loss, we actually end up with a significant amount of money less. And that's because these were big gains and big losses. If I said a 1% gain and a 1% loss, you would still have less money, but it would be a significantly smaller damage. You'd probably be in like the 99,000, 98,000 range instead of the 75,000 range. So a lot of people will think, oh, if I gain the same percent as a loss day back to back, that all right, I'm going to be back to where we started. But that's not the case. And sometimes, again, with these large numbers, it can be a drastic change. So let's work on B now. I have to erase my screen, unfortunately. So let's just hold on to this $75,000. I'll rewrite that on the screen in just a second. So for A, we had $75,000 in the end, and we were sad face. For B, what if the gain-loss order was reversed? Do you think that gaining or losing the money and then gaining the same amount of money, is that going to give us a different amount in the end or the same amount in the end? Let's find out, because the answer to A was probably unexpected. A lot of people probably expected to be $100,000. So maybe switching this order will have an effect on the answer. So for part B, now again, we're swapping the gain and the loss. So our new amount, oops, I want to write Monday first. For Monday, our new would be the old of $100,000. And we're going to take the hit first. So times 1 minus the 0.5. We're taking the loss first, which is 100,000 times 0.5. 1 minus 0.5 is 0.5. So that's just half of 100 grand, which is 50,000. And that's how much we have on Monday. Ooh. So that was a big hit. We just lost 50 grand. But for Tuesday, now the $50,000 is our old for Tuesday. And we're going to get the 50% gain. So we go equals, sorry, not equals. The new is equal to the old amount, which is the 50 grand, times the growth factor, 1 plus 0.5. Again, growth is add, decay is subtract. Well, that's going to be 50,000 times 1.5. Half of 50 grand is 25 grand, so 50 times 1.5 is 75,000. So that's how much we have at the end of Tuesday, the close of market Tuesday, if you will. So this is the same outcome. We're still sad. We are equally as sad. It's just funny because it feels very different. With scenario A, we go from 100 to 150 to 75. So we get really excited when we see that 150,000 number, but then we end up taking a big hit. With the Tuesday version, by taking the loss first and then the gain, by dropping to 50,000 and then getting back up to 75, you probably actually feel a little relief on Tuesday because you're like, okay, well, at least I'm not down to 50,000 anymore. But it's funny because the outcome is exactly the same. It's really interesting how the order of things occurring, especially with these stock market gains and losses, can make you feel different even though the outcome is the same at the end. Now, some people will draw a little too much of a conclusion from this and they'll say that, all right, it doesn't matter the order of gains and losses over your 30 or 40 or 50 years of being in the stock market. And that's not actually true. This problem, we had the same starting balance and we never added anything into it. When you have a proper retirement fund, like I hope you all end up getting at some point sooner than later, hopefully, you're continuously adding money to this pile, and having a big gain or loss early in your career is a much smaller effect than later in your career, because early in your career you may only have $5,000, $10,000 in that account, and losing half of that, like you may have lost 30% right now in the past month because of the stock market going into a bear market. If you lose half of $10,000, you can continuously add for another 30 years, and that effect is going to be minimal. But if you're retiring in a week and you lose 50%, you are going to feel that like nothing else in the world. If you've got $1 million and on the next to last day you're in the market, you lose half of it, now you're at 50 grand, that definitely has a significant effect on you. Which is why I don't want to say we because I'm not a financial advisor. That is why people advise to be less aggressive in the stock market, the 3 to 5 to maybe even 10 years before you're getting ready to retire. Whereas people that are younger can be super aggressive and take a 30% hit, like some of us may have done. I might be raising my hand right now. But I got a long time to work, so that effect's not going to be too drastic. So I really love this problem right here. I really do, because it shows how percent changes affect each other, and that going up and down the same amount doesn't result in the same thing. But the order that it occurs, as long as you're not adding to the pile, actually doesn't have an effect. Even though going through that roller coaster in your personal life you may feel different if you went from gain to loss, then loss, then gain. All right. Let's clear our screen. Back to annotate. Now I have a little note here. It says see example intent in text. We're not going to do that. I can't even pull up the textbook right now. Sorry for that. Pause for a drink of water. However, we are not done with this section. I want to do something from the worksheets. Let me make sure I pull up the one that doesn't have the answers first. Okay. I'm looking for page. Sorry, I thought I had it on the right page and it's not. Here we go. Hold on. Give me 1 minute. This is not the page I want. So when I say that, I'm looking at my worksheets, not what you see on the screen. My pages aren't lining up directly with this. Okay, here we go. Now I'm good. Use the Census Bureau report, Income and Poverty in the US for 2017 table from the previous guided activity showing income in 2017 dollars for households. Compute the total and percent difference in the number of family and non-family households in 2017, where those numbers are in thousands. Do this in two ways, switching the order in the arrow diagram. Okay, remember earlier I was talking about with percent change with new and old. In order to call something new and old, you have to have some sense of time as a reference. So like the year 2017 versus the year 2018. And we had a lot of that in the problems we were just doing. Old salary, new salary. Old salary, new salary. Old salary, new salary. Oh, 2018 versus 2017, old versus new. Monday and Tuesday, old and new. What we're getting into here is that everything is at one specific time. We're not comparing an old and a new. We're comparing family versus non-family numbers. So we're comparing family versus non-family numbers from a table above. So I'm going to have to pull up that table in just a second. So we can't say that family is old and non-family is new. That doesn't make sense. We can't say that non-family is old and family is new. There's no sense of time, so we have to be told what the order we should do it. So what order they tell us to do it? They said to do it in two ways. So one time, we're going to call the family the new, the family the old, and the non-family the new. Then we're going to flip the script, and we're going to call the non-family the old and the family the new. So what we're going to see is what a percent change feels like if we start with the family first or if we start with the non-family first relative to one versus the other. And we kind of saw this happen when we compared boys and girls in a previous problem where it was like 2 boys and 3 girls or 3 boys to 2 girls, something like that. So family versus non-family, and we got to pull up our table, which is back here. Can I zoom in on this? Yes, we can. All right, so family, and we're looking for 2017. So all of these numbers are 2016, which means we are not using any of those numbers. We're using the 2017 number. So don't even look at these left 3 columns for number of thousands, estimate, and margin of error. We're not going to use the estimate. We want the actual number. We don't need the margin of error column at all. We do not need that column at all. We're using, let me pull up my annotate. Make it red. So we are using only this column of values from 2017 and the actual number, not the estimate. Some of these estimates are drastically off. So we were comparing family to non-family, the total family to non-family. So if you look over on this left side, we got a whole bunch of little individual categories. They have it categorized by age, by race. But here we have type of household, here's family households, and here's non-family households. So again, we're not looking for individual married or individual female, household or no husband, male household or no wife. We want the total family, which is this 83,088 number. So this is the family number. Then we need to get the non-family number, which, let's see, we have our non-family over here, not the females, not the males, all of them, which is this 44,498. So those are the 2 numbers that we're going to use, 83,088 and 44,498. Let me write those down really quickly just so I have them on my piece of paper. Okay, so now let me scroll down. So the family number we said was the 83,088. And then the non-family number we said was the 44,498. And then we need to calculate the total change and the percent change. So we're calling the family the air quote old value and the non-family the new value. Again, the idea of old and new makes no sense with this, but we can still do the math involved. So the total change is what goes up top. As a reminder, the top's total change, the bottom one is percent change. Total change is just the subtraction. So that's going to be the 44,498 minus the 83,088. Four four 498 minus 83088. And that'll give us negative 38,590. So the total change is negative, meaning it's a decrease. 38,590. Remember, it's always new minus old. And again, the new and the old we have just described as family and non-family. So that was a decrease. Now the percent change is supposed to be the total change divided by the original, the old, the thing that air quote happened first, which we have called family. So again, this is what we're calling the old. This is what we're calling the new. They're not really new or old, it's just the labels we're calling them. So our percent change, it's the ratio of the total change, which is that negative 38,590, divided by the original, the old, which was the 83,088. And when we do that division, 1,590 divided by 83088, we'll get 0.46 something, 0.4644. Move that decimal right twice, and you'll get 46.44%. And that's a negative, by the way. I forgot my negative symbol. Negative. And rounded to the nearest tenth, that would be negative 46.4%. So that is our percent change if you think about the family being the old value. So the non-family relative to the family has a 46.4% change. That means it's smaller by 46.4% of the family's value. That's what that means. Now, unfortunately, I'm going to have to erase my screen because I need to scroll down. I wish I had just done this a little different, but that's okay. So let me get these numbers back up here. Family 83,088. The non-family was 44,498. Sorry for the quick scribbles. We found a total change of negative 38,590 and a percent change of negative 46.4%. Now what we're going to do is swap what's relative. So now we're going to say, what's the family change relative to the non-family? So we're going to pretend like the non-family is the old or the original and the family is the new. So now we got 44,498 on the left is the old. The 83,088 is the new. So our total change, the difference of them, 83,088 minus the 44,498. This number should look familiar, except it's positive. You're going to get 38,590. And I mentioned that last class a week ago that total changes, if you swap old and new, they're just opposites of each other. So that's an increase, a little plus sign, of 38,590. So the family, there are 38,590 more family people than non-family. Whereas over here, we were saying there were 38,590 less non-family versus family. Making the percent change, we're going to take the total change of positive 38,590 divided by the original, the old, and now this time we call the old the non-family. So 44,498. We're dividing by a smaller number this time. Dividing by smaller numbers makes outputs bigger. And when you do this division, 38590 divided by 44498, you end up with 0.86, 0.8672. I'll do 4 decimal places again. Moving it right twice gives us 86.72%, but rounding to 1 decimal says it's an increase of 86.7%. So there are 86.7% more family members than non-family members. That's the interpretation here. There are 86.7% more family members than non-family members. So that's what question 2 gets in. Use both of these percent changes in sentences. So again, I'm going to have to erase these so I can scroll down. But going from family to non-family, it was 46.4. Going from non-family to family, it was an increase of 86.7. It sounds more serious going from non-family to family. So let me just scroll down a little bit. Put those numbers back up. So this was the minus 46.4%. This was a up 86.7%. So those are the numbers we need for our sentence. So from the first part, going from family to non-family, that means there are 46.4% less non-family compared to family. But the second problem says that there are 86.7% more family compared to non-family. So when there's no sense of time, when we are allowed an arguable choice here and whether we're comparing one to the other, which one we're calling the old, which one we're calling the new, if you want to make these numbers sound bigger, you can. If you want to make these numbers sound smaller, you can. And it's things like this that lead to, dun dun dun, fake news, or at least scare tactics in general. So again, because these problems did not have a sense of time, we were comparing thing A to thing B, particularly family to non-family. In the real world, you could choose to call family the old. In the real world, you could choose the non-family to be the old. If you want your percent change to look bigger and maybe scarier, or maybe bigger and more positive, I don't know, it just depends on the concept, then you would prefer the plus 86.7% answer. But if you wanted a smaller number for whatever reason to make it sound maybe scarier, maybe better, depending on the context, did I just say betterer? I think I did. Betterer, more betterer. So you could say that family is what we're comparing to. The total change doesn't really feel different. That subtraction, it's just a matter of whether it was plus or minus. But those percent changes with that relative concept, because of the fraction dividing by the original, it changes the number. Okay, so that will close out 4.3. We're going to skip the next problem. I just mainly wanted to get that one. Oh, I know what I want to do next. Quiz question. What is a farm animal that clucks? What is a farm animal that clucks? Someone just said this is hard. All right, so what is a farm animal that clucks? That is your quiz question, and a duck does not cluck, that quacks. So that is your quiz question. I think that we'll all be able to answer that. It doesn't matter if you answer it with an uppercase or a lowercase, it will accept both. Just make sure that you spell that word that rhymes with pickin' very carefully. All right, so that's how quizzes will work in this class, completely randomly in the middle of the lecture. That way you have to watch the whole thing. All right, so again, answering in the chat is not going to do anything for you. Make sure you go to Canvas and answer it under the quiz section, and it's due tomorrow by midnight. Okay. .4 data tables with percentages, and we will definitely not finish this today. But we have to get into an important concept, and another one of those things where media likes to misrepresent information for fake news, scare tactics, whatever it might be. This percent change concept, we've been doing this where the original values were numbers. So like a dollar amount, or just an amount. It didn't have to be a dollar. A number of family members, a number of apples and oranges, whatever you might want to talk about. But we can also do percent change calculations with values that start out as percents. So this is for numbers that are given as percents. So we don't give you actual numbers originally for the old and the new. We give you percent amounts for the old and the new, like in this example below. Bob earns a 2% pay raise in 2018. He earns a 4% pay raise in 2019. What's his total change in percent change in pay raise? I never gave you a dollar amount. I gave you percent amounts. This problem might feel a little more confusing, and the answer is definitely going to be a little weird, but what's all this other stuff say? Percentage points are a total change of a percent, and they're abbreviated with the symbol PP. So whenever you are given a problem where the old and the new are percents, you are going to need to use the phrase percentage points or the symbol PP to represent the total change. Now here's why. In the past section, a total change was just a difference of amount. So it was like a dollar amount or a number of people. Now our total change is going to be a percent, but then the percent change will also be a percent. That's confusing. We don't want to have a total change and a percent change be represented as percents, because then if I just say, all right, the change was this with a percent symbol, you can't necessarily say whether it was a total change or a percent change. So this is what you're going to see used, and this is used in the media as well when they use it appropriately. Now, does the media always use symbols appropriately? Absolutely not. I can't promise that ever. But in our course, we do need to use that symbol. So when you're writing a total change where you're taking a subtraction of percents, please write that answer with a PP instead of a percent symbol to avoid confusion. When you go and do your percent change, that's when you'll still write a percent. So this right here is nothing new. A percent change is a relative change. We've discussed that before. And then all caps, the thing I just said 2 or 3 times, do not list a total change with a percent symbol as it's confusing. Use the symbol PP. You may see a single P every now and then. I've seen this written many different ways in media, as you might expect. So let's try out this example. Bob earns a 2% pay raise in 2018. That's pretty much just a cost of living adjustment. Then he earns a 4% pay raise in 2019. So he probably got a cost of living adjustment and, hey, you've done a good job. Here's a little extra. Or maybe inflation was higher in 2019, so his COLA raise was higher. Or maybe it's just a really nice company that always gives raises. Cough, don't be a state employee. You don't always get raises. Cough. All right. So total change and percent change. These formulas are literally the same as before, and I will copy paste them one more time. Remember, you are supposed to memorize these. So there's our total change and percent change formulas. Total change, still just the difference in new and old. Percent change, the ratio of the total change to the original, converted to a percent. So our total change new minus old. Oops, I'm trying to write in the wrong spot. The 2% was what happened in 2018. The 4% is what happened in 2019. So the 2% is the old, the 4% is the new. So new minus old, new minus original, would be 4% minus 2%. 4 minus 2 is 2. So that is 2%, but we said to always use PP to represent the total change when your total change is a percent. So 2 percentage points is how we need to phrase our total change. You also may be given a problem where they say the total change is 2 percentage points. The new is this, what's the old? So you'll be able to tell that it's a total change because of the symbol PP. We will never tell a percent change with this symbol. It's always for total change. So that means that our pay raise was 2 percentage points higher in 2019 versus 2018. That means our pay raise got a bump itself. The pay raise is a bump, and our bump got a bump. For the percent change, this is where we take the total change, which we just calculated, and divide it by the original. So the total change is what we just calculated as 2 percentage points divided by the original, the old, which was the 2%. Now, a percentage point is literally the same thing as a percent. The percent symbol means the same thing as percentage point. We only use this to avoid confusion. They are the same thing. This is just to avoid confusion in reading and writing. So what that means is percentage points and percents cancel each other out. So this is just 2 divided by 2. It's unitless, which is 1. That is not a 1% pay increase because that's a decimal. Moving the decimal right twice gives us 100%. So our salary rate increased by 100%. What? What in the world? No, our pay raise was 2% and then 4%. What is this 100% thing talking about? Well, relative to the pay raise we got in 2018, the raise we get in 2019 is an additional 100% of that old raise. 100% of 2% is 2%. So we're getting the old 2% plus another 100% of that. So 2 and 2 make 4. Now, media, of course, which of these numbers are they going to want to use? Well, if they want to scare people, if they want to act like some company is giving these ridiculous raises year over year, they'd say, oh, TCC, and this is never going to happen, TCC just gave their pay raises 100% increase in comparison to the previous year. That sounds insane. It sounds like people are going from making $50,000 to $100,000 a year when it is not the case. It means that we went from a 2% raise to a 4% raise because we're talking about an increase on an increase. It's kind of like Inception. So news would love to say, oh man, everybody got a 100% pay raise compared to last year. And that's a relative statement because I said compared to last year. But in reality, they're getting a 4% raise this year, which happens to be 2 percentage points higher than the last raise. So a change of 2 percentage points here, that feels like a small change. But relative to the last one, you're making 100% more in terms of an increase. And you could throw in an old salary number and go from there and find out what happens after year 1, after year 2, to see that that effect is not something insane. But again, these numbers just feel very different. The relative change sounds scary and like something that the mass media would love, or if you're the employee, it sounds like you're being misled. Whereas this total change feels a little more appropriate. But again, in our world, just because something's appropriate doesn't mean that's what people use. So this PP symbol is very, very important. I've seen lots of students just rush through things, not pay attention, not try and understand, not memorize, and they'll swap the symbol, or they'll just go, well, what is a PP? I've never seen this before. Yes, you have. If you watch the lecture, if you do the homework, yes, you have. Okay. This next problem is a little more interesting. it's not really having to do with this idea here. We'll do more of those next time. But let's close out today with just kind of a more of a quantitative reasoning idea. This relative size is what's important here. A sobering problem. Drunk drivers, and this is a statistic I looked up about a year ago, drunk drivers are responsible for 33% of motor vehicle deaths. Now, that means that 67% of motor vehicle deaths are caused by sober drivers, because between the two, they have to make up 100%. 100 minus 33 is 67. All right, so drunk drivers cause a third of all motor vehicle deaths. And this statistic may have just been for America. I believe it is just for USA. This means that 67% of all motor vehicle deaths are caused by sober drivers. So 1/3 of deaths are caused by drunk drivers. And I believe that's probably throwing just inebriated drivers in as general. So maybe not just alcohol. And then the other 2/3 of all motor vehicle deaths are caused by sober drivers. Why do we not worry about them? And by them, I mean sober. Why do we not worry nearly as much about the sober drivers? Well, what are the sober drivers doing that's causing these deaths? Well, one big one in the modern age is texting and driving. Maybe even eating or drinking and driving. Eating or drinking. So multitasking just in general. Multitasking is always bad. Even just talking. If you've got a group of people in your car, 3 or 4 people, and you're having a good old time, it could be a distraction and you can get an accident. Just general, my favorite thing in QR, paying attention or not paying attention. Medical conditions, etc. There are a whole lot of different things I don't need to lay out that a sober driver can cause an accident that leads to a death, either their own or the other car. And we are saying that for every 1 accident caused by a drunk driver, there's 2 caused by a sober driver. But why do we focus so much on drunk driving? We are a world that says, do not drunk drive, do not drunk drive, do not drunk drive. Shouldn't be driving over 0.08 or at 0.08. Arguably shouldn't be driving at all. We don't need to get into the semantics of the percentages and everything of your BAC. Why do we focus so much more on drunk drivers setting up DUI checkpoints, et cetera, versus sober drivers? And that's not to say that we don't focus on sober deaths. We definitely have been trying to eliminate texting and driving in the past few years. We definitely encourage people not to multitask and drive. If someone has had seizures, we tend to take their licenses away if they're repeat. I don't want to say offenders, that sounds wrong, if they have seizures irregularly. But we still talk so much more about, I still need more space. There we go. About the drunk drivers. It's all about relativity. Think if you were to go on the road on a normal non-COVID-19 day, and this is still hopefully true of even today, just a lot less people driving right now. How many of those people are drunk at 9 a.m., 10 a.m., 11 a.m., noon, 5 p.m.? Most people on the road at those times are sober. So on the average time of the day, your driving population probably looks like this. And I'm going to use kind of a set notation. This is our entire driving population of the sobers and non-sobers. So this ellipse represents 100% of all drivers on the road at any moment on average. Now, yes, there are more drunk drivers on the road at midnight, 2 a.m., New Year's Eve, days like that, but we're just talking about averaging everything every time. So if this big, I was about to say circle, ellipse represents every single driver, all drivers, in terms of how many people are drunk on the road on average, it's a really, really small population. So this little circle inside of it That represents the drunk drivers. Maybe it's 1% of the population, maybe it's 5% of the population driving, maybe it's 0.1% on average. I don't have an actual statistic, but you can definitely say at any time, especially daytime, there are a lot more sober drivers than there are drunk drivers. And it's this relativity that is why we worry about the drunk drivers a lot more. So this teeny tiny little population right here is causing 33% of deaths. 1% of the population, 2% of the population, a half a percent, a tenth of a percent, somewhere in that ballpark. Those are the percentage of people causing a third of the deaths. Whereas the other 99, 99.8, 99.1, 98 point whatever percent, they're causing 2/3 of the deaths. So this little population is completely chaotic, and that is why we worry about the drunk drivers so much more than the sober drivers. And again, I'm not saying we don't worry about the sober drivers. We definitely try and eliminate texting and driving by creating laws against it. It's been discussed that multitasking in general shouldn't be done. If you have underlying medical conditions, you might have your license revoked just for the safety of yourself and others. So I think this is an interesting problem because, again, without actually doing any math, just thinking about population size and them one relative to the other, you can really see why this is such a drastic issue. Imagine if half of this population were drunk drivers. I would say they're probably going to be causing 99% of the deaths at that point. And please, I hope we don't ever live in a world where 99% of the drivers on the road are drunk. That sounds awful. Okay. So we are done for the day. We did not finish 4.4 as I suggested. We will finish that next class, which means we will have finished the material for the midterm. Remember, the midterm is going to cover chapters 1 through 4. So I will be getting your review materials for that very soon. And then your midterm will be posted in my math lab. I will have dates for all of that stuff next class. So again, the 4.2 and 4.3 homework are due in a week. I do not have any Excel assignments assigned currently. You will get another one next week. And I'm probably going to give you a little bit more time to work on that since the midterm's coming up. And your project is also due on the 7th or the 8th, whichever that was. The due date's in Canvas. I believe it's the 8th. I'm fairly certain it's the 8th. Right, remember that we probably had a quiz question earlier, so make sure you go and answer that in Canvas. Remember, that is graded. It's a simple 1-point thing. I can't imagine anyone watching this video doesn't get that point. Please don't misspell the answer. That's the only thing you can mess up. Don't put any extra spaces or anything like that. Besides that, have a good day. We will see you on the internet on Wednesday, same math time, same math channel. I'll upload this to YouTube in a little bit in case you need to rewatch anything. Right. Have a good afternoon.